Hey math fans, Alex here to you today with a problem from the 1995 Putnam Exam. This is problem B3, and it says the following: to each positive integer with n squared decimal digits, we associate the determinant of the matrix obtained by writing the digits in order, left to right and top to bottom. For example, for n equals 2, for the digit 8617, we're going to go ahead and write the 8 here, the 6 here, and then the 1 here, and then the 7 here, and calculate the determinant to be 50. So for a 2 by 2 matrix, to calculate the determinant, you take 8 times 7 minus 1 times 6. Find as a function of n the sum of all possible determinants associated with all n squared digit integers. Okay, so anytime you have a leading digit, we're going to go and assume that it's non-zero. So otherwise, for things like numbers like 0, 5, 1, 10, we don't sum that. Okay, so that's not included in our sum. Okay, so I argue to you that there are actually 3 cases, and I'm actually going to do what you might consider the most difficult case first. Okay, so n could be one of 3 things in this case. So case 1, we're going to go and let n be greater than 2. So we're looking at the sums of all possible determinants of all possible 3 by 3 matrices where the upper left-hand digit is non-zero. Okay, so let's just remind ourselves how to find the determinant of a 3 by 3 matrix. Okay, so for example, if I have the digit, we'll say 1, 2, 3, 4, 5, 6, and perhaps 3, 2, 1, that's going to be associated, since in this case we have 9 digits, so n equals 3, for example, has 9 digits, and that's going to be associated with the square matrix, and we have to find the determinant of the matrix 1, 2, 3, 4, 5, 6, and 3, 2, 1. Okay, another way to symbolize this is to, instead of writing the curly braces right here, we could write it in kind of these absolute value braces, although we're not, of course, taking the absolute value. This is just another symbol for the determinant. And let me just remind or show you how to find the determinant of a 3 by 3 matrix. So this works for any n by n matrix, by the way. What you do is you start with this number. I guess I should highlight this number, right? So we start with 1. And we're going to multiply that by the determinant of the 2 by 2 matrix formed by crossing out this column and this row. Okay, so we're going to be left with this 2 by 2 matrix, and we're going to multiply this times that determinant, so 5, 6, 2, 1. Okay, and now what you do is you just go along either a column or a row, but every time you introduce a new number, this next number, which I'll go ahead and highlight, has to be a negative. Okay, so that's the thing with these determinants. Has to be a negative. So we go along right here, and we're going to take that times the determinant of the 2 by 2 matrix formed by canceling this column and this row. Okay, so we have that 2 by 2 matrix. So we're going to have the numbers, So we're going to have the numbers 4, 6, 3, and 1. Okay, and then we alternate signs a final time, and then this is going to be plus, and then 3. I suppose I could do in, this color times the determinant of the 2 by 2 matrix formed by canceling out this column and this row, namely this one. Okay, so we have the determinant of 4, 5, 3, and 2. Okay? And then, the idea is that you should be able to find these determinants, right? Okay, so this is 1 times, and then 5 times 1 minus 6 times 2 minus 2 times 4 times 1 minus 6 times 3 plus 3 times 4 times 2 minus 5 times 3. Okay, and then you can simplify it from there. Okay, so that's an example of how it would work for a 3 by 3 matrix. So why am I considering this case first? This seems really difficult to find the sum of all possible determinants of all possible numbers. Well, it's actually not. This is actually the easiest thing in the world if you know one little property about determinants. So, this is going to be, I don't know what this is going to be. This is going to be some number. Okay, maybe we'll call it like X or something like this. And that's just one number. However, is there a way that I could maybe manipulate the order of these numbers a little bit and have the determinant be not X, but negative X? Okay, because if I switch the order of these numbers a little bit, that's still a distinct number. If I can get that to be negative X, then the sum of those two cancels to 0. And it turns out there is. Okay, so I'll state this as a fact. So fact. Swapping 2 rows of a square matrix changes the determinant. I'm just going to abbreviate that DET, the determinant, by a factor of -1, which is exactly what we wanted, right? Just in orange, by a factor of -1. So if the determinant of one matrix is X, and you just swap 2 of the rows, which you should always be able to do, then the determinant of that is -X. And now we have a way of doing all of these simultaneously for n greater than 2. Doesn't matter the size of the matrix. You swap just 2 of the rows and you automatically get a determinant where in the sum it's going to cancel them out as pairs. Okay, so what that's going to be is that I don't really know what the determinant of this matrix is. I called it X. Right, so I guess, summary, the determinant of, what did we say? 1, 2, 3, 4, 5, 6, 3, 2, 1, I don't know, that's X. But what I do know is that if I swap these 2 rows, because this is associated with the n squared digit 1, 2, 3, 4, 5, 6, 3, 2, 1. If I just go ahead and swap the middle and bottom rows, so this is 3, 2, 1, 4, 5, 6, the determinant of that is -X, and that's associated with the number 1, 2, 3, 3, 2, 1, 4, 5, 6. And you can always find such a corresponding pair. The only perhaps tricky part is, well, what if this number is 0? Well, you just wouldn't consider it, right? You just wouldn't consider it at all. Okay, but, let's say that I have a number like 0, 1, 2, 3, 4, 5, 6, 7, 8, right? Well, I wouldn't be able to consider that number, so it just wouldn't have a corresponding pair. I don't need it to have a pair. Okay, but for any number that you name, there will always be a distinct number that will cancel with it that we can consider. So we do them in pairs, all of which will cancel. So in the case that n is greater than 2, so for n bigger than 2, the sums of the determinants of square matrices the sums of the determinants of all square matrices with, I'll maybe put a caveat here, but the sums are all 0. And of course what that caveat is just, the upper left digit is non-zero. I mean, you could have something like 3, 0, 4, 5, et cetera, but you just can't have a 0 in that first place, is what that problem was saying. Okay, so we actually eliminated every single possible case except 2. Either n is 1 or n is equal to 2. And those are easy enough to figure out. Let's do n equals 1 first. I consider that to be the second easiest case. So we'll do case 2. I know this is kind of backwards of how cases usually work, but I'm doing them in order of difficulty. You might argue this is easier than the n is greater than 2, but we have more energy in the beginning anyway, right? Okay, so for n equals 1, we're considering 1 squared by 1 squared determinants. Sorry, not 1 squared, but 1 by 1 matrices, which are just scalar values, right? It's technically a rank 0 tensor or whatever you want to call it. But if n is equal to 1, what you have is the sum of all possible 1 by 1 matrices. We exclude this, right? This isn't counting, but then we have that matrix, which is just 1 plus this matrix plus yada, 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 plus the determinant of this matrix. Guess I should put determinant in front of all these, shouldn't I? Okay, but this matrix is just the same as the scalar, and the determinant of a scalar is just that scalar. I don't know how you want to think about that. You could essentially factor the 2 out, and then you have the identity 1 by 1 matrix, whose determinant is 1. Doesn't matter how you want to think about this, but you're just summing the numbers 1 through 9. So I could just go ahead and do that by hand, but instead I'm actually just going to go ahead and show it to you like this. So from k equals 1 to 9 of k, remember that Gauss's formula tells you that that is k, k plus 1 divided by 2. No, not k, n, excuse me. Where this is n, this is your stopping number. Not to be confused with the n in the previous problem, but Gauss's formula says that this is equal to 9 times 9 plus 1, all divided by 2. So that's important because I'm going to use that. Okay, which in our case, I believe is 45. All right, so that's part of the answer. If n is equal to 1, then the sums of all the determinants would be 45. And now we just have to consider one more case to finish out this problem, and that is, well, what if n is equal to 2? Well, that's a little tricky, right? Because for instance, if I have, the digit, 6049, this is, again, just an example. If I have 6049, that's going to be the determinant of this matrix. And I can't pull the same trick, right? I can't just say, oh, well, go ahead and fix this and then swap 2 rows. Well, the only 2 rows to swap would be these 2. Right? And I guess you could try to make an argument for, well, if this determinant is equal to x, then I could just swap these 2 rows. So that was my line of thinking when I first approached this problem, right? So let's say the determinant of that is x. I can go ahead and swap the rows, and then I get 4960, and the determinant of that is negative x. And so these cancel out when you add them together. And while you would be correct, let me just throw a wrench in that plan. Let's look at this example. 3410. So the determinant of that is, it's going to look like this. However, if you flip-flop the rows, what you end up getting is 0134, which we are not including. Remember? We're not including anything that starts with 0. So you can't really pull the same game right here because there's no guarantee that the lower right-hand number is non-zero. So yeah, unfortunately, you can't play the same game. So I'll just, I guess, cancel this out because we're not, yeah. However, what we can say is the following. So I'm going to go ahead and consider the determinant of all matrices of the form, we'll say A, B, C, D, where A is non-zero, and I'm going to sum all possible determinants. Well, the way to do that is just to take a quadruple sum. So I'm going to take 1, 2, 3, 4, and here A has to go from 1 to 9. Here B goes from 0 to 9. C goes from 0 to 9, and D goes from 0 to 9. This looks really complicated. It's not as bad as you think. And again, this is just the way that I approach the problem. Maybe you approach it differently. Okay, but the determinant is very simple. It's just A times D minus B times C. Okay, so this is equal to, I really don't feel like writing this again. Okay, so this is equal to that times, yeah, maybe I'll highlight this. So the determinant of this guy is equal to AD minus BC. Okay, and how are we supposed to evaluate this sum? Well, you would distribute the sum, right? You distribute the sum to each of these terms. There are just two terms. Okay, so what that's going to get you is, let's see. I'm glad I copied that one thing, right? So this would just be this times, we'll say AD minus this times BC. Okay, and now what I have to do is, what I can say is that this A can sneak out as a constant from all of these summations except this last one. Okay, so I can factor the A out as a constant and I'll be left with, let's see, this will be the sum from A equals 1 to 9 of A times the sum from B equals 0 to 9 times the sum from C equals 0 to 9 times the sum from D equals 0 to 9 of D. Okay, and then I can really just pull the same game, right, with this. Okay, the A is kind of left alone in our case, but then I have the sum from B equals 0 to 9 with the B, and then I can pull the C out of the first sum, and I get C equals 0 to 9 of C, okay, and then the sum from D equals 0 to 9 of just 1, really. Okay? So, what I have is I have two kinds of terms. I either have the sum from 0 to 9 of 1, or I have the sum from 0 to 9 of just the number itself. You say this is the sum from 1 to 9, but that's the same thing as the sum from 0 to 9, the term itself. There's really no distinction there. Okay, so what I can do is recognize that the sum of 1, if I just keep repeating 1 9 times and adding that up, is going to be 9. Or actually, it's going to be 10. Because we do start at B equals 0. Okay, so my bad. So let's see. This is going to be 10. This is going to be 10. This, according to what we just did in case 2, was 45, right? Just the sum of 1 through 9, that's 45. And this, again, is also 45. Okay? And now we play the same game, except this term right here is very importantly not 10, but it is in fact 9. Okay, so this is 9. This is 10. Or sorry, 45. So we have a B there. This is 45, and now this is 10. Okay, so finally what we have is we have that this is going to be 10 times 10 times 45 squared minus 9 times 10 times 45 squared. So I can lastly factor out the 10 times 45 squared. Let's see, and I'm left with 10 minus 9, which is just one of these terms. So I have, okay, let's just write it out. 10 times 45 squared times 10 minus 9, which is 1. Okay, so then I have 10 times 45 squared. Okay, I don't know what 45 squared is off the top of my head. That's just 40 plus 5 squared, which is 40 squared plus 2 times 40 times 5 plus 5 squared. I know if I were a competitor, I would memorize these squares, but I don't. I don't do this. I do this for fun. Okay, which is 2025. So 2025 times 10 is 20,250. Okay, so what's the final answer? And this is kind of the reason that I don't love this problem, because it's, in my opinion, it's misleading, because it says find as a function of n. And I understand that constants are technically constant functions, but it's misleading. When it says find as a function of n, it makes you think there should be an n in it, when I personally, when I did this problem and I checked with the answer key, like there was no function of n at all, okay? So my final answer would be, I don't know, f of n is equal to, let's see, we got what, 45 for n equals 1, 20,250 for n equals 2, and 0 otherwise. Okay, so I would say that's my final answer. Hope that was helpful, and have a great rest of your day.